For this lesson, we're going to do hypothesis tests for a mean when we do not know sigma. Now, you all know we have to have a standard deviation to do a test, but the standard deviation is going to come from the sample, and this is going to be a t-test. All right, it says, in a recent study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was 2.2 kilograms with a sample standard deviation of 6.1. Can we conclude that the mean weight loss is greater than 0? And I'm going to do a test at the 0.05 significance level. Now, notice it says sample standard deviation. Even if it didn't say sample, and if it didn't say S, that is still sample standard deviation. Remember, it has to say sigma to be population. So this is not sigma, this is sample. So I'm going to do a t-test. All right, my conditions, same ones. The first condition is that they did an SRS, and they probably did not do an SRS. That's why they didn't put that. They probably, in this problem, randomly assigned groups based on the weight loss. Like, half of them were on this low-fat diet, and half of them were on Weight Watchers, something like that. My problem didn't say normal, but N is greater than 30. So CLT tells me that my sampling distribution will be normal. My HO and my H1. H1 is, can you conclude that the mean weight loss is greater than 0? Mu is greater than 0. HO is mu is 0. It's nothing special. I'm going to list out my data. I've got my X bar is 2.2. My S is 6.1. And my N is 76. I'm not going to list alpha because it's 0.05. That's what it typically is. My HO and my H1. My H1 is, can I conclude that the mean weight loss is greater than 0? HO is going to be 0. When you do this problem, we're going to do this one by hand, and then we're going to switch to the calculator. Here's how I'm going to get my test statistic. It's going to be based on the student's t-distribution, and it's going to be X bar minus mu naught, the same as with Z. The difference is I'm going to use the t-distribution, and I'm going to use S in place because I don't have sigma. All right, so my X bar is going to be 2.2. My mu naught is going to be null hypothesis 0. My S is 6.1, and my N is root 76. I'm going to go to my calculator. I'm going to type 2.2 minus 0. Now, you wouldn't have had to type the minus 0. I just wanted to remind you about the parentheses. Divided by 6.1 divided by root 76. All right, and my T is going to be 3.144. You will find that on the T distributions, a lot of times the T's go past 3. Remember, there was more area at the tail. All right, I'm going to draw my T up here. And I'm going to put a 0, and I'm going to put 3.144. And I want to find this area. So on my calculator, I'm going to go to distributions because I'm going to do the math. I'm going to do a student's T. I need my DF for this. Remember, every student's T is different based on the sample size. So my DF is going to be 76 minus 1, 75. And I'm going to do a right tail test. And I want the probability X is greater than or equal to 3.144. And note that my probability is real small. My picture doesn't match that, but it doesn't matter. My drawing was just to help me on the calculator. It's 0.0012. And that is your p-value. All right, if the p-value is low, HO is going to go. That is a very low p-value, so we are going to reject HO. So here's what we're going to say for our conclusion. I'm going to say, since our p-value of 0.0012 is less than alpha equals 0.05, we will reject HO. All right, if HO is gone, and you can take your pencil and like lightly go through HO. HO is gone. You're going to conclude H1. We have enough evidence to conclude the true mean weight loss, you want to say true, is greater than 0 kilograms. In other words, this diet worked. Then you want to interpret the p-value. So I'm going to say, if HO is true, our whole problem was based on HO is true. If HO is true, there is a 0.0012 chance of a test statistic as extreme or more extreme than ours. And ours was at T equals 3.144. All right, and like I said, in the next problem, we're going to move away from the math and we're going to move towards the calculator. So what I want you to do, everyone pause your video and read this problem, please. To start this problem, we're going to go to the calculator and we're going to input our data into our list. So go to statistics and input your data. All right, and once we've done that, I'm going to start my conditions. Now, notice that this has a really low alpha level. All right, so we want to be careful with that. So here are my conditions. I've got an SRS, and the data set's too small for CLT, and it doesn't mention normal, so I'm going to graph it. And when you graph it, it looks fine, and it's always going to look fine. And what we're going to say is no outliers or strong skewness, normal, check. All right, and I want to know how strong is the evidence that the mean amount absorbed differs from 3.5. Now, differs is two-tailed, so I'm going to highlight this too so we don't forget it. And HO is going to be just, it doesn't differ. It is 3.5. All right, so I'm going to go to my calculator. I'm not going to do distribution this time. I'm going to do inference. I want the calculator to do the math. I'm going to do a test, and I'm going to do one mean, and I'm going to do a t-test. My null hypothesis is 3.5. My alternate is not equal to. I'm going to use my data set. Notice it's going to automatically pull it up from that list. My significance level is 0.01. And when I get to here, what I need is that p-value and that test statistic. So here's going to be my screenshot. And I did a one sample t-test. And I need my test statistic. I need my t, negative 2.951, and my p-value, 0.0256. Now, my p-value is low, so my first thought is that HO is going to go. However, that p-value is not low enough for this alpha level. So here's what I'm going to say. I'm going to say since my p-value of 0.0256 is greater than alpha equals 0.01, we will fail to reject HO. If you fail to reject HO, it's not going anywhere, so you cannot conclude H1. So we will fail to reject HO. We do not have enough evidence to conclude the true mean amount absorbed differs from 3.5 micrograms. All right, now when you interpret the p-value, it's a little bit different where it's two-tailed. So I'm going to say, if HO is true, there is a 0.0256 chance of a test statistic as extreme or more extreme. And you want to say in either direction or in both directions. That's what's different as ours. And ours is t equals negative 2.951. All right. Now the next one. Pause the video and read this problem, and then we will. This problem, I want to know if I can conclude that the vendor's claim is false. All right, so here's what we're going to do. My conditions are SRS. It didn't say anything about normal in the story, so I'm going to say N is greater than 30. CLT normal. And this one, the vendor's claim was that it would crash less than 6 times per year. All right, so his claim is less than 6. To conclude that his claim is false, I'm going to say no. I think it's greater than 6. Okay, so that's concluding that his claim is false. So H1 is going to be mu is greater than 6. Again, his claim is false. And HO is going to be mu is 6. And I did not give you one on Alex where you had to switch it like that. But this time, like I said, they're asking if his claim is false. I'm going to go into inference. I'm going to go all the way back to make sure I end up with the right thing. And I'm going to do a t-test. My null hypothesis is 6. My alternate is greater than 6. I'm going to input my statistics. And I didn't write down my data this time. You don't have to. The sample mean was 7.1. The sample standard deviation is 3.6. The sample size is 41. Now the significance level, remember we changed it last time. This time it's back to 0.05. And I'm going to go to next. And I forgot to show you something last time on the calculator. I'll show you this time on the calculator. And remember how you can check your answer. All right, I'm going to go to next. Hold on, I'm going to go back one. That was what I wanted to show you. Now, here's what I've got. I'm doing a one sample t-test. And my T is 1.957, and my p-value is 0.0287. And notice each time I'm rounding it. Now, the p-value is low, so HO is going to go. So here's what I'm going to do. I'm going to say, and if you want, go like that and lightly cross out your HO. So I'm going to say, since my p-value of 0.0287 is less than alpha equals 0.05, we will reject HO. We have enough evidence to conclude the true mean number of crashes is greater than 6. And I'd like you to put and the vendor's claim is false. You would not have to, though. Now, interpreting the p-value, if HO is true, there is a 0.0287 chance of a test statistic as extreme or more extreme than ours. And ours was T equals 1.957. Now, on your calculator, go to the next screen and zoom in on this. Hit your plus sign on your calculator and zoom in. And look at your p-value. And look at your alpha value. The alpha is the dashed. My p-value is well inside of that critical region. It's much less than alpha. Therefore, I should reject, and I did. So we did the right thing. A couple other things with this section. I want you to look at what we tested. Now, I had changed the alpha level to 0.01. On this part of the problem, it's going to be 0.05. And if it was 0.05, we would have rejected HO. All right, now what this is saying informally, where we reject HO, we're saying 3.5 is not plausible. Now, once you look at this, that's 0.05. This is a 95% confidence interval, and I want you to look at how it does the same thing. The confidence interval is this, and the confidence interval does not contain 3.5. So 5%, 95%. The confidence interval does not contain 3.5. So 3.5 is not a plausible value for mu. The confidence interval tells us the same thing. Now, this next thing, I want to talk more about our errors. A type 1 error occurs if we reject HO when it's true. It has to be true in order for it to be an error when we reject it. A type 2 error occurs if we fail to reject HO when it's false. And I'd like to make the probabilities as small as I can of these errors. Now, the probability of a type 1 error is equal to your alpha level. So if you have an alpha level of 0.05, the probability of making a type 1 error is 5%. If you look back at our problems, like on this vendor claim, the probability was 5%. The one before that, the probability was 1%. That's a chance of a type 1 error. Now it says, because alpha is the probability of a type 1 error, why don't we always choose a very small alpha? And that's because the smaller your alpha is, the larger your value is of beta, which is the probability of a type 2 error. And I want you to draw a couple of these betas. So beta, you start at the bottom and it looks like that. And that's a probability of a type 2 error. Now, typically type 1 is more serious, which is why a suitable value of alpha is chosen before the test is performed. But the smaller I make my alpha value, so if I take my alpha down, my beta goes very, very high. All right, so looking at this problem, Charlie will perform a hypothesis test at 0.05 alpha level. Felice will perform the same test at the 0.01 level. So Charlie has a 5% chance of a type 1 error. Felice has a 1% chance. Now, if you look at this, it says if HO is true. The only reason it's telling you that is because HO has to be true to make a type 1 error. That really doesn't matter for this problem. It says who has a greater probability of making a type 1 error, and that is Charlie, because he has a 5% chance. Now, if HO is false, the same thing. It has to be false for type 2. Who has a greater probability of making a type 2 error? And look at Charlie and look at Felice. Felice made her alpha level really, really low. That brought her beta level up. So this is Felice. All right, and that's how you determine who has the higher chance based on your alpha level. This just talks about you always want to give your p-value because everyone doesn't agree with your alpha level. If I see your p-value, I know, okay, based on my alpha level, I would have not rejected, or I would have failed to reject, or I would have rejected. So that's why you want to do that. And sometimes just because something is statistically significant, it is not practically significant. For example, say you studied and studied and studied and studied, and what you did, the new way you studied was statistically significant, but it took you hours and hours and hours, and it only brought your score up 2 points. It might not be, and it might not be practically significant for you. So that's what they mean when they talk about that. And that's the end of our lesson, hypothesis test for a mean when we do not know sigma.